Hi, the lecture today is going to be about separable ODEs. I'm going to start with this topic because it's particularly simple and directly connects to calculus. And so among all the techniques that we are going to see, this is probably the one that is most familiar to you. Before we start with the differential equation itself, let me just remind you of some basic facts of differentiation. So you remember that if you have a function of the type, for example, say x cubed plus x plus 1 to the power of 10, to differentiate this, you utilize the following power rule. If you have an expression raised to the power of n, then the derivative of this is the exponent times the expression to 1 less whole power times the derivative of that expression. So if you want to take a derivative of this thing, it would have been 10 times x cubed plus x plus 1 to the power of 9, and then derivative of the base, which is 3x squared plus 1. In particular, if we see an expression where we have a function of a function and we want to differentiate it, then we have to apply the chain rule and then find the derivative that way. Let's go ahead and take an example. Suppose I have a relationship which is, say, y to the power of 4 plus y squared, and say plus y is equal to, say, x to the power of 5 plus x plus 1. There was a topic in calculus under implicit differentiation where you would be asked to find the derivative, that is, find, for example, dy dx. And this example that we are taking is special case of that. So on one side I have some function of y, another side a function of x, and I want to differentiate and find the derivative of y with respect to x. Pretty much everybody is familiar with differentiating x to the power of 5. That is, you know, this is the derivative 5x4, and then derivative of 1 is derivative of x is 1, and derivative of 1 is 0. When it comes to the left hand side, many students make a mistake of taking the derivative by just writing 4y cubed. That is incorrect because we are differentiating y with respect to x, and differentiating y with respect to x is just like differentiating u to some power with respect to x. So the derivative here is 4y cubed times y prime, and here is 2y y prime, and here the derivative of y is just y prime. You might be wondering why on the other side we don't write x prime. It would be perfectly right to write x prime here, that is to write 5x4 x prime, but x prime means dx dx. dx dx, in this context, x prime dx dx is just 1. That's why on this side we don't have a x prime. Otherwise, same rule actually applies to both sides. At any rate, again, in implicit differentiation, when you are coming across this special case, on this side you can factor y prime easily. So y prime factors, we get 4y cubed plus 2y plus 1. On the other side we just have 5x4 plus 1. And then we can write y prime, which is again just dy dx, is 5x4 plus 1 over 4y cubed plus 2y plus 1. And then in calculus the issue will be taken further perhaps by asking you to find the equation of the tangent line and so on. Anyway, that was an exercise in calculus 1. If you take this exercise and walk it backwards, meaning from this end stage you go back to this starting stage. That is just what we call solving a differential equation by the method of separation. Only very special cases can be solved in this way, and it is essentially our lucky day if that's the method that's applicable to our problem. So notice how the answer looks in this case. I have a function of x here and a function of y here, and I am multiplying or dividing them, and on the other side I have y prime. Let's go ahead and start this problem again from scratch and take another example, see how we solve this. Suppose I have the following question. Derivative is given dy dx, and it is given as, say, let's take a simpler example, 3x squared over say 1 minus 4y cubed. The question is solve this. So this is just y prime, it's 3x squared over 1 minus 4y cubed. We call this thing separable, so we say this equation is separable because by multiplication and division I can take all of my y's to one side and all the x's to the other side. So I can write this thing by cross multiplication, 3x squared dx on the right side. At this stage the equation is separated, and I can now say I'm back in the calculus territory and I can integrate both sides. Well, typically these integration processes are straightforward. Integral of 1 is just y. Integral of 4y cubed, well, that's y to the power of 4. And each of these integrals have a constant. Let's call this constant, for example, k, or any letter like that. Derivative of 3x squared, that's x cubed. And I have a constant here as well. Well, believe it or not, we are at the end of our problem. This is the solution. Typically, they clean it up a little bit more by merging the two constants in one constant and writing it on either side. For example, I can write this as a y minus y4 is equal to x cubed plus c minus k. Simply k was brought to the right hand side. Now c is unspecified constant of integration, k is another one, and the difference of them is still another one. So I can merge these two and say y minus y to the power 4 differs from x cubed by some constant. I might call this thing any letter. So for example, I might write c minus k is, say, constant m. So in all of these problems, c, k, m, and so on are constants. Now what is it that we got so far? What we have is called implicit solution. So this is going to be the answer to the problem. Rather mysterious as to what this thing is, because we haven't seen equations of that type all that often, but whatever it is, this is our solution. And because of its peculiar look, it's called an implicit solution. Well, you might ask, what do you mean implicit? What is meant by explicit? Explicit solution is when either y is given in terms of x, or less commonly x is given in terms of y. If that is possible to be found, then we press forward for finding an explicit solution. So explicit solution refers to the case that you have y is given as a function of x. That's a tradition to express y as a function of x. Sometimes you might want x as a function of y. Whatever it is, either case, it has to be stated in the midst of solve. Now, an issue that we have is more often than not, that's not really easy to achieve. That is, like finding y in terms of x, in this case, requires solving a rather complicated equation, in this case a quartic equation, and the solution of that is going to fill a couple of screens full of this monitor that I have. It's not really useful to go after such a complicated expression as an item left for other classes, and in fact, if the equation that we were dealing with was any more complicated, we wouldn't even have that one either. So we are going to go after something a little bit more realistic. We are going to go after graphing software that's going to give us an idea about what the solution might look like, and give up on that luxury of having a nicely defined function. So what do we do for graphing? One of the tools that we are going to use in this course, and I like you to practice it, and there would be information about it on my website, is something called Desmos. It's a very nicely prepared software. You go to desmos.com, and it's very easy to use, probably much nicer than any graphing calculator that you have. So for example, over there I had y to power of 4 minus y is equal to x to power of 3, and then I space, and then I have the software is smart enough to understand that you have certain parameters in your equation, and here they are called a slider. So slider gives you a choice of a value to be assigned, and then the graph will be drawn for that particular value. So when I click on slider for m, it by default it starts at m equal to 1 and then draws the corresponding graph. We notice that this graph is not something that we see every day. It's not doesn't have a name or something. It's just a graph. We could have spent quite a bit of time as a problem in calculus to graph this thing and find certain specific information about it, but well, that was a problem for calculus, and we are beyond that, and then we assume that you already studied this thing in calculus, and here we want to move on and get some items from differential equation done as opposed to items from calculus. So on here you can use this slider, and as you change it, you notice that the corresponding graph is graphed for that particular value m. So for example, here m is 6.6. If we replace m by 6.6, the graph of this equation is going to be what you see here. And then you can of course go to the other direction. You will notice some other appearance at, say for example, minus 7.7. If you want to control the behavior of this slider, you can always click here and assign a starting value, ending value, the increment step, and you get a more refined picture perhaps. If you want to see an animation of this equation for different values of m, here's how you play the animation, and then it goes back and forth between your assigned values and gives you a graph. So you get a quick description of what the function actually behaves like. So sometimes this is going to help you quite a bit in answering questions in the homework that you have. Let's go ahead and let me stop this thing, and we go back to our lecture and continue. So if you come across this kind of equations, first line of defense is to get the implicit solution, and if the homework presses on for some explicit solution, then you have to take additional algebra steps if that's possible to find the corresponding equation. So for example, in this equation, it would be relatively easy to find x in terms of y. That doesn't take much of an effort. So if I take m to the other side, y minus y4 minus m, and take cube root of that of this, then that is x in terms of y. Somehow in our calculus classes, there's y is described in terms of x, but in fact it's just quite legitimate to give x in terms of y. So here is such a solution. But as we said, finding y in terms of x, it is a major challenge. Make sure you don't confuse the situation. Just moving y4 to the other side, it's not a solution of y is a function of x, like meaning if I take y to the power of 4 on this side, this is not y as a function of x, as a function of x, y, because y again shows on the other side of this equation, and that is a no-no when you're describing a function. Okay, let's go ahead and try a few other examples. Suppose we take say y prime is equal to x squared over y. Less crowded than the previous one. Now just remember to write y prime. First of all, what's the meaning of that? That's dy dx. We have to be clear in our head as to what the prime means in any particular situation. So I have x squared over y, and then what we do next is we typically multiply and divide as needed. Like in this case, I have y dy is equal to x squared dx. Next, we have the integration step. So at this step, we have y squared on this side, x cubed on the other side, and then this is y squared over 2, and this is x cubed over 3. And then we can allocate a constant to either side. We said really each side has a constant, but they can be merged into one. So I can write this thing is x cubed over 3 plus a constant m. That is going to be my implicit solution. Well, this case is clean enough, simple enough for us to go ahead and attempt an explicit solution. So for example, I can multiply by 2. This becomes 2/3 of x cubed plus, let's say, 2m. And I can take square root. Now we have another complication that when you take a square root, you get possible plus or minus. Now, in a typical problem like this, some additional information is going to be given to us that's going to help us to decide as to which one of these two is applicable to our problem. As the problem is given, it could be either plus or minus. But how is that additional information is given? Typically, that is given in the context of initial condition. What is the initial condition? Well, we said differential equations come from physics. In physics, we have the concept of initial condition. For example, if you are holding a ball and you want to throw it, you decide where to throw it from and at what speed to throw it. Those are initial conditions that specify the trajectory of the ball. You choose a starting point and you choose a starting speed, and then you kick the ball accordingly. Well, in mathematical examples that imitate this, we have also an initial condition. For example, we might say solve y prime. We're going to look at the same problem, y squared over y, x squared over y, subject to for example, y of 1 is equal to 2. What does that mean, y of 1 is equal to 2? This is a shorthand for saying that when x is 1, y is 2. So this is referred to as the initial condition. In physical applications, typically they say at time 0, meaning at the beginning of the experiment, the startup conditions are such and such, like position is this or velocity is that, and so on. Well, it doesn't have to be always at time 0. It could be at any starting value. So for example, here is at time 1 or at x1, y has supposed to be 2. What does this mean? It means 1 and 2 are supposed to be a point of this solution that we have. So I just take this problem. Suppose we have gone as far as any of these stages. For example, I pick this one. It doesn't really matter which one you pick. So let's start with that. Y squared is equal to 2/3 of x cubed plus 2m. Typically, at the very first stage of solution, we go ahead and apply our initial condition. So either this or that would have been pretty good. So I have my y taking the value of 2 and my x taking the value of 1. So I plug them, these two values, in my equation and find m, and then proceed accordingly. So if y is equal to 2, this is going to be 2 squared. This is equal to 2/3 of 1 cubed plus 2m. So this is 4 is equal to 2/3 plus 2m. Therefore 2m is going to be 4 minus 2/3, and that is 10/3. So if you want m itself, is going to be 5/3. I put this value back in my equation. I get y squared is equal to 2/3 of x cubed. I had a 2 and m is 5/3. So I have y squared. If I clean it up, I have 3, 2x cubed plus 10. If I take square root, it appears as if I still have the plus and minus. But a moment's reflection shows that, in fact, I have easy way of telling if I have to choose plus or minus. The way I decide that, I say this is the initial condition that must be satisfied by my final solution, that when x is 1, y has to be 2. So instead of y, I put 2. Here's a question mark if I'm supposed to have a plus or minus. My x is 1. Well, 2 times 1 cubed plus 10 is 12. Divided by 3, that's going to be 4. Square root of 4 is 2. And of course, I need a plus sign here for the two sides to be equal. With minus sign, they will not be equal. So I figure out that my solution is, in this case, plus 2x cubed plus 10 third. And of course, I don't need to write the plus, so I can just erase that. It's assumed to be. So that what I've received now is an explicit solution. When you are doing the homework for this section, you have to be clear as to what is explicit and implicit solution, and just go as far as needed for finding the answer to the problem, and then you'll be done. Okay, let's do a few more of these problems so that we have practice from, essentially this amounts to practice from calculus. Really, there is now not much concept from differential equation here. It's just the concept of derivative and integration, and that's about it. So let's go practice one more example of this. So here we say solve. Now y prime is equal to x squared over y times, let's say 1 plus x cubed. Well, by now we are familiar with the steps. This is to be replaced by dy dx, and here I have my right hand side. I just copy y times 1 plus x cubed. Commonly it's very obvious as to what to do, so I multiply by y here really. So I have y dy is equal to x squared dx over 1 plus x cubed, and all that is left to do is to integrate both sides. By now we learned we just put the constant on one side. Y dy, antiderivative of that, well, no problem there. We know that from calculus. On the right hand side, we are facing one of the challenges of calculus, which is how to find the integral or antiderivative of an expression. You have gone through plenty of exercises in calculus 1 and 2, and as I mentioned last time, you need to take a look at your calculus book, refresh your mind as to how you go about finding derivatives and integrals. And here's one of first examples that we come across this issue. What is the antiderivative for the right hand side? So what you want to do, pause, think for yourself what the answer is going to be, and then when you are ready, come back. So this is one of the places that we are going to need to press that pause button. It's really important that you do some of these things yourself to get into shape for this course. So I hope you took a pause and then came back. So the way to handle this problem is by u substitution. We notice that the derivative of denominators is closely related to the numerator, and that's a clue as to what substitution to use. So if I use u is 1 plus x cubed, then du becomes x 3x squared dx, and then this integral simplifies for me. X squared dx is du third, and the denominator is u, and this thing is 1/3 of logarithm of absolute value of u plus a constant. So we said this constant is absorbing the constant from both sides. So I can write the right hand side 1/3 of logarithm of then u was 1 plus x cubed, and then a constant. Now if we want to find y in terms of x, that is relatively easy. You multiply by 2 and take square root. You can also find x in terms of y, and that is not all that complicated. So I leave that to you to work out. Let's do one more exercise of this type, perhaps a little bit more complicated. Let's okay, suppose I have y prime is equal to, say, 2x over 1 plus 2y, and we also specify y of 2 is equal to 0, and that's our initial condition. We are going to abbreviate this from now on. Initial condition, you're going to IC is going to stand for initial condition in our problems. So again, I invite you to solve this problem by yourself. So pause. Should be able to solve this problem in at most like 4 minutes or something. And let me ask for 2 steps. One is to give me the implicit solution, and slightly more challenging part of this thing, get me the explicit solution. And we have to specify y in terms of x, meaning y is on the left side of your equation and the right side is just populated with x. Okay, I hope I convinced everybody to actually do this by themselves, and then you come back. So here I'll be a little bit faster than before. dy dx is 2x over 1 plus 2y. Next step, 1 plus 2y dy is equal to 2x dx, and then integrate. So now I have y plus y squared is equal to x squared plus c. As soon as the constant appears, if the initial conditions are given, we try to nail down the constant. Let's just remind ourselves who is what. This 2 is x, and you see that y is equal to something. That is what our y is going to be. So if y is replaced by 0 and x is replaced by 2, then c should fit in that equation. Well, obviously c turns out to be minus 4. So far we have y plus y squared is equal to x squared minus 4. So what do I have now? I have the explicit solution. Excuse me. I have the implicit solution. Again, if you have come this far, again I insist you stop the video and find out y in terms of x. What is y equal to? Well, typically students get perplexed as to what to do next. They take a y squared to the other side and so that's the solution and such. Remember, we want to give y on right hand side must be purely in terms of x. There shouldn't be another occurrence of y on the right hand side. So how do we approach that? Well, in this particular case, we consider this as a quadratic equation and just solve it. That is, I write these things as a y squared plus y, and then I bring this term to the left hand side, so it becomes 4 minus x squared is equal to 0. So I brought everything to one side. Now this is an equation that's very familiar to you. That's a quadratic formula. Let me remind you of a quadratic. So let's write the quadratic equation in some other letters so we do not get confused. Suppose I have AW squared plus BW plus C equal to 0. Here's the celebrated quadratic formula known to humanity for several thousand years. W is minus B, plus or minus. Should I pause again? I'm sure everybody is familiar with this. B squared minus 4AC divided by 2A. Now everybody is familiar with that from high school, but sometimes people forget that A, B, C don't have to be always given numbers. They could be parameters, and still you can apply this formula. So my A here is 1, my B is 1, and then this 4 minus x squared, this whole thing is my C. So if you realize that, then finding y will be easy for you. You just say, well, I'm just going to plug A, B, C in the formula that I have here. Minus B, that's minus 1, plus or minus B squared, so that's 1 squared, minus 4 times A, which is 1, times C, and that is where sometimes students are perplexed with, that they think C has to be just a number or a single letter or something. No, this is standing for any expression. Any mathematical expression could be sitting for A, B, C. So long as you realize that, then you got it made. So I have twice A comes here. So I have by now minus 1 plus or minus 1, and then multiply through minus 16 plus 4x squared over 2. So I have y as minus 1 plus or minus expression 4x squared minus 15 over 2. Are we done? Well, let me pause again, or ask you to pause. Are we done? Well, not really. Just one tiny step left. Finally, what is the answer? With a plus or minus? Did you remember from last time? How did we say we solved this? Your final answer should subscribe to your initial condition. And so if you have plus or minuses, you check yourself which one of the answers that you have actually agrees with the initial condition. You just choose that. So if I have x2, y0, this specification, what choice does it give you between plus, or how does it decide for you between plus and minus? So if I put 2 here for x, 4 times 4 becomes 16 minus 15, that's 1. To force a 0, I have to have minus 1 plus 1 to get 0. So I'm forced to choose minus 1 plus radical 4x squared minus 15 over 2, because this is the only one that when x becomes 2, y simultaneously becomes 0, and we are satisfying the initial condition. So the chosen answer turned out to be plus 1. Okay, so we went through some of the basic examples of implicit differential equation. So you're going to have a set of exercises based on these basic problems. There are still some other problems in this section that are slightly more complicated, and the complication is going to be really related to topics from calculus. So to practice our calculus topics, we are going to have in the next video some more advanced problems. But as separable differential equations go, the technique is very obvious. You just bring all the y's to one side, all the x's to one side, integrate, and you're pretty much done. From there on, what is left is essentially issues of pre-calculus or calculus, and that makes you to take a look back at your calculus book and see how to proceed. So let me stop this video here and ask you to solve some of the homework problems that are going to be assigned, and then the next video we are going to continue with some more advanced topics on the same issue of separable method. Okay, so good luck and God bless until our next meeting.